This is CS50, and this is the end of week 4. So some good news and some bad news. So no lecture on Monday, no problem set next week. You're not going to like where this is going. But we do have this instead next Wednesday. And there's also, per the syllabus, one Friday lecture next Friday so that we can stay on track. But everything will be filmed as usual, so not to worry. And with regard to Quiz 0, what we'll do toward week's end is post on the course's homepage, CS50.net, an explanation of what sort of expectations you should have when it comes to the first quiz. In general, it will be multiple choice, true, false, short answer, short coding problems. You're not going to be expected to implement the equivalent of a problem that you would see on a P-set, for which you have a computer and a debugger and the like. But there will be small coding problems. And indeed, the best guide to get a sense of what CS50 quizzes are like is go to CS50.net, go to the quizzes link, and you can see the past several years' worth of quizzes. Just realize the curriculum has not always been the same over the years. Sometimes we add, sometimes subtract. So if you see some topic on one of those old quizzes that you have no idea what it's talking about, it's either that we did cover it or that we didn't cover it, but in the form of reviews this Sunday, Monday, and Tuesday, as well as a course-wide review session on Sunday night. Time and location to be announced on the course's homepage. You'll have an opportunity to review with the course's teaching fellows the material for this year, both in section and as a full class. And those will be filmed as usual as well. All right, so without further ado, one comment on pass, fail, and add, drop. So you may have seen my note last night, and this is really just as an additional reassurance that if you are among those particularly less comfortable or somewhere in between and you're feeling just a little bit in over your head, realize that is indeed quite normal. And there's an ample support structure in place, one of which office hours were intent on improving all the more per my email last night, and realize too that an option like pass, fail for a class like this really is meant as a mechanism to take the edge off of a course like this. So that again, if you're spending those 10, 15, 20 hours just trying to get some P-set to work, and you know you're 90, 95% of the way there, but you can't find some damn bug, you know, in a pass-fail model, that's sort of okay. The idea is that you can, with that mechanism, you can then go focus on your other P-sets or sleep or whatever it is that you want to focus on. So realize that you have until this coming Tuesday, technically the 5th Monday, but it's a holiday, so this coming Tuesday to switch from pass-fail to graded or vice versa. And if you're really on the precipice and are thinking of dropping altogether, please catch me after lecture, drop me a note. We'd love to at least chat before you bid adieu. All right. So we started taking the training wheels off last time. In particular, we focused on string. String is something that's declared in the CS50 library, specifically in that file called cs50.h, which we'll start to look at this week and next. But string is really just a simplification of something that's a little more arcanely described as char star. So char we're familiar with. It's just a single character. But star, as of Monday, denoted what? A pointer. And what's a pointer? So it's like an address, a location in memory. What's an address or location in memory? Well, again, all of us have laptops with a gig or 2 gigabytes of RAM most likely these days. And that means you have 1 billion or 2 billion bytes worth of memory. And it doesn't really matter what it physically looks like, but take on faith that you can number all of the individual bytes that your own laptop has. This is byte 0, this is byte 1, this is byte 2 billion. And that's exactly what a computer does. When you allocate space for a single character, for instance, it obviously has to live somewhere in your computer's memory, and maybe it's at byte number 1, 2, 3, 4, 5, and that's somewhere up here in your computer's memory. And the address then of that character is 1, 2, 3, 4, 5. Now, in week 0 through now, thus far, we haven't really cared where in memory things are stored because we usually use symbols, variables, and arrays to actually get at our data. But as of Monday and all the more today, you're now going to have all the more expressive capabilities with writing programs to really manipulate a computer's memory however you see fit for both good purposes and bad, bugs being a very common result at this point in learning this stuff. But what does it really mean to be a char star? Well, let's go ahead back to, and we'll come back to Binky as promised today. Let's go to a simple example here. Let me save this file as compare.c. And let me just get some template code here. So include standardIO.h. Let me also give myself include cs50.h. I'll zoom in up there. Let me start writing main int main void. And now I want to do something like this. Printf give me a string. And then I will use string s gets get string to get a string from the user. Then I'm going to ask the user for another one. Give me another string. And I'm going to ask them via getString to get that. I'll call it t, because t comes after s, and s is a nice name for a string if it's pretty generic. So getString. And now I just want to do a sanity check. And I'm going to say if s equals t, then I'm just going to tell the user, printf, you typed the same thing, new line. Else, I'm going to print out something like you typed something different, or whatever the sentence will be. So something like that. Then as usual, I'll return 0, which just signified that nothing bad happened. And I'm going to go ahead and compile and run this program. But on Monday, we ran this program and actually were told that hello is not hello, and goodbye is not goodbye. The behavior we saw was a little more like this. Let me go into my source directory, zoom in here, and let's do make compare. Compiled OK. Let me run compare. Give me a string, hello. Give me another string, hello. You type something different. Well, let me try something simpler like 50, 50. Type something different, hi, hi. So clearly something's going on here. But what was the explanation for why apparently line 12 is completely dysfunctional? What's the fundamental problem here? Yeah. Yeah, exactly. It's actually comparing the addresses in which hello and hello are stored. It's not comparing the letters, H-E-L-L-O, again and again. Because what's really happened, well, all this time as we've been using getString, we have this blackboard is, again, our computer's memory. And let's say I call getString after declaring a variable s. What does my memory look like? Well, let's arbitrarily say that S looks like this. It's a square. And pretty much any time I've drawn a piece of memory on the screen, if it's 32 bits, I've been drawing squares like this. Because indeed, in the appliance, a pointer, an address, is 32 bits. It's the same as an int. That can vary based on computer system. Those of you who are vaguely familiar with the fact that your computer, your Mac or PC, is 64-bit, that actually denotes that your computer is using 64-bit pointer, 64-bit addresses. And among the upsides of that is that your computers can have much more RAM than yesteryear. Long story short, back in the day when computers only used 32 bits to represent addresses, the biggest number of bytes you could represent in that case was what? If you have 32 bits? So 4 billion, right, because 2 to the 32 is 4 billion. This number has been recurring in the course. So if you only have 32 bits, the highest number you can count to is roughly 4 billion. But that was a fundamental limitation of computers until a few years ago, because if you can only count as high as 4 billion, it doesn't matter if you buy 8 gigabytes of RAM or even 5 gigabytes of RAM. You can't count that high, so it was useless. You could only access the first 3 or 4 gigabytes of your computer's memory. That's less of an issue now, and you can buy MacBook Pros and Dells with 8 gigabytes of RAM or even more these days. But if I allocate quite simply in this program a pointer, a pointer called s, it might look like this on the screen. Because indeed, we need to peel back this layer. I keep saying string, but as of Monday, string is really char star, the address of some character. So let's take that training wheel off, even though we'll continue using getString for now. So I've declared s, and this is a chunk of memory, 32 bits. What's in here in memory by default? What's that? Garbage, exactly. If you, the programmer, do not put a value in a variable, who knows what it is? Sometimes you get lucky and it's 0, which is kind of a nice clean default value. But as we saw Monday, sometimes it's complete nonsense, some really big positive or negative number that came from where? Yeah. Yeah, often the function that got called before. Because remember, as you call functions in memory, they take up more and more space from the bottom up. And as soon as the function returns, that memory gets reused by the next guy that gets called, who's using your same slice of memory. And if you've left garbage there, previous values, well, we might mistake s as having some value when really we haven't put anything there. So our RAM at this point looks like this. Now on the right-hand side of line 7, we're calling getString, which we've been doing now for weeks. But what is getString really doing? Well, getString, written by the CS50 staff, is a little intelligent in that as soon as the user starts typing keys and hits enter, getString figures out how many keystrokes did the user hit, how many characters do I need to allocate RAM for. And where that RAM comes from, who knows? It's somewhere in your computer's 2 gigabytes or whatnot of memory. But let's suppose that the computer found space for the word hello right here. And the word I typed was H-E-L-L-O. And if we draw this as a sequence of characters, we might draw it like this. But I need to do one extra thing. What belongs at the end of any string in C? The null character, which we write as \0. It's technically the number 0, but the backslash makes all the clear that this is literally the number 0, the integer 0. It's not, for instance, quote unquote 0 that you might type at the keyboard. So this is hello. And what did we say on Monday? That a function like getString is actually returning all these weeks. It's not returning a string per se, because that doesn't really have meaning, because strings don't exist. They're sort of a fabrication in the CS50 library. What is really a string more technically? Exactly. It's quite simply the address of the first character that the user typed in. So if my word hello ended up at byte number 123, and then at byte number 124, 125, 126, and so forth, if I just number my bytes from 0 on up, well, what really getString is returning is literally the number 123. So what gets put in S is the number 123. Not the letter H, not the word hello, quite simply the address at which I can find the first letter of hello. But that doesn't seem like enough. I asked you for a string, not a character. So how do we or the computer know that E-L-L-O kind of come along with the H? What's the sort of agreement we have? Yeah? Exactly. There's just this human-computer convention whereby when you are dealing with strings, otherwise known now as char stars, you simply have to figure out where the end of every string in life is by really just iterating over it with a for loop, a while loop, whatever, so that when you find the end of the string, now you can infer from that, oh, the whole word was H-E-L-L-O. Those of you with prior programming experience might know in Java, you can just call .length. And in other languages, you just can call length or similar. Well, that's because in a lot of languages, especially things called object-oriented languages, the length of something is kind of encapsulated inside of the piece of data itself, much like we encapsulated IDs and names and houses inside of a student on Monday. But C is much lower level. There are no objects or classes. If you've heard those terms before, all you have really is memory addresses. So this is sort of the old-fashioned way of representing interesting data structures. You have a start value, like the address of the first character, and then just some arbitrary convention that everyone agrees to follow. So how is string length implemented, did we propose? Strlen, S-T-R-L-E-N, which some of you have now used a few times. It's pretty simple, right? It's like 2 lines of code. It's pretty much a for loop of some sort, maybe with an additional local variable. But Strlen just has to take a pointer and then start looking for \0. And as soon as it finds it, it can return the total number of steps that it's taken in that string. So we can infer from this what goes on next. Suppose then I declare T, as I've done in line 10. This is some garbage value, who knows at first. But on the right-hand side of line 10, I'm calling getString again. Who knows where this ends up? Let's arbitrarily say that the operating system found room for it way over here. I happen to, coincidentally, type H-E-L-L-O again. And so we can draw the same kind of picture. But the fact that I've redrawn this picture is deliberate, because that is a different H-E-L-L-O than this one. So here, this might be location 4, 5, 6. This is 4, 5, 7, and so forth. So what gets put where the question mark once was? In this case, 4, 5, 6. Now, we're picking these numbers arbitrarily, because really after today, we're not going to care so much about what the address of anything is. All we care about is that we can figure out the address of some piece of data, like hello. So really what most people do in computer science, when talking about memory addresses and talking about pointers specifically, rather than bother figuring out 1, 2, 3, who cares where this stuff actually is? We just know that it is at some numerical address. We simplify the world and just say that S is pointing to that character and T is pointing to that character. And the fact that it's an arrow is quite intentional, because literally now S is pointing at H and T is pointing at the other H, because at the end of the day, it doesn't matter what the address is, but it does matter that we have the ability to express that address with some piece of code. Now, we haven't really manipulated these addresses just yet, so we'll see where we can interject and sort of do things with pointers. But for now, in line 12, literally, what values are we comparing according to this story in line 12? We're saying is 1, 2, 3 equal to 4, 5, 6. And that's definitely not the case. And even conceptually, this pointer is definitely not the same as this because you called getString twice. And getString does not try to be super clever. It doesn't try to realize, oh, you typed hello 5 minutes ago. Let me give you the same pointer as I gave you before. It just allocates a new chunk of memory each time you call it. So how do we fix this problem? If higher level, I want to compare the strings hello and hello. I don't care about the pointers. How do I go about answering the question, did the user type the same thing? What's necessary here? Yeah. So I can use a function out of the box. I can use a function called strcmp, strcmp, just the abbreviated version of saying string compare. And if we go into, for instance, compare to, which is among today's handouts, I do exactly that. I kept everything else the same from line 1 on down to 26 or so. And now notice this part has changed just a little bit. Let's ignore line 28 for a moment and focus only on this one. What did we say Monday that strcompare does? Well, it handles the process of taking 2 pointers, S and T in this case, sort of virtually putting its finger on those 2 letters. And what it must do is something like a while loop or a for loop. And it says, are these the same? If so, it moves the fingers or the pointers forward. Are these the same? 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 And oop, I'm at the end of the string at both S and T. I haven't found any contradictions. Yes, these strings are the same. And what does strcompare return if 2 strings are the same, apparently? 0. So 0 is good in this case, because if it returns -1 or +1, that means that S just happens to come before T alphabetically or after T. And why would that be useful, to have a function that tells you which string comes before or after in a dictionary? Searching and sorting. So you can do things like binary search or bubble sort or merge sort, where you have to compare things. Thus far, we've kind of cut some corners and only talked about sorting in the context of numbers, because it's nice and easy to talk about. But you can certainly compare strings, apple and banana, because if apple is known to come before banana, similarly can you move strings around in memory, just like Rob did with merge sort in the video, and we did here on stage with selection sort, insertion sort, and bubble sort. So where else can we take this? Well, let's try this. Let's sort of forget that lesson for a moment and try now in copy1.c to do the following. In line 21, I'm saying print something. Then I'm getting a string from the user. Then I'm checking this. Now, we haven't really gotten into this habit yet, but let's now do this. Let me actually simplify, or let's actually peel back this layer. This is really char star. This guy is really char star. So what does it mean to be checking if S equals to null? Well, it turns out that when you call a function like getString, or more generally, just ask a computer to give you some memory, something could go wrong. You could be crazy and ask the computer for a terabyte of memory by asking for, trillions of bytes of memory that just don't exist in the computer. But getString and other functions need some way of yelling at you if you've asked for too much. And the way getString does this is if you have asked for more memory than is available in the computer, even if that's super, super low probability, because none of us are going to type 1 trillion characters and then hit enter, but low probability though it may be, I still want to check for it just in case. And the special value that getString and certain other functions returns if something has gone wrong is null, in all caps. And what is null? Null just so happens to represent a pointer. It's memory address 0. The world decided that arbitrarily, if this is my computer's memory, you know what? We're going to steal just 1 byte of every computer's memory. And this is location 0. We're going to give it a nickname of NULL. And we're going to promise that we will never actually put real data there, because we just arbitrarily need a special value, 0, aka null, so that we can yell at users if something goes wrong. Otherwise, you might not know, does 0 mean put something here, or does it mean something went wrong? We have to all agree that null means nothing was returned. No actual address was returned. Now here, I'm just adopting my human convention of I return 1 from main if something goes wrong. That's because main's return convention is to return 0 if good, 1 if, or some other value if bad. But getString and any function that deals in memory returns null if something goes bad. OK, so unfortunately, line 27, super simple though it is, completely fails to copy the string. Why? Well, we can see this as follows. I'm claiming in line 27 to be making a copy of S and calling it T. So I'm not asking the user for 2 strings this time. I'm just saying the value in S should be put in T as well. So now just to demonstrate how broken this is, in line 29 onward, what am I doing? Well, first I'm checking if the length of T is greater than 0. There's some string there. The user typed something in. What is line 32 doing, apparently? Right, you can kind of infer it from what I said is it's doing. But technically, what is this doing? T bracket 0 represents what? The 0th character, or more human-like, the first character in T, whatever that is, H maybe in this case. And 2 upper does what it says. It capitalizes the 0th character of T, and it changes it. So this means take the 0th character of T, make it uppercase, and put it back in that same location. So if I type H-E-L-L-O in lowercase, this should change the lowercase h to a capital H. But the problem is that in line 35 and 6, what I'm about to do is print out for us S and T. And what's your hunch? What am I actually going to see if I typed in H-E-L-L-O in all lowercase? What's going to get printed? What's that? The big H and the rest small for which? S or T? Both. Exactly. So let's see what's going on here. Let me go ahead and compile this. So this is copy 1. So make copy 1. All right, zoom in. Let me go ahead and run copy 1, enter, say something, H-E-L-L-O in lowercase. It capitalized the copy, but it apparently capitalized the original as well. Because what now happens in this story? Well, in line 27, I don't actually seem to be copying the string. But even though you might have intuitively hoped that to be the case, if you think about this picture, what really have I done? Well, half of the picture is the same. So let's roll back in time so that T does not yet exist in this story. S can exist in this story, but let's lowercase hello this time. So let me fix what I actually typed in. So in this case here, we have H-E-L-L-O. We'll draw it as a sequence of characters. Put my separator lines here and my \0. So this is where we are as soon as line 1 through 24-ish, give or take, have executed. This is the picture of my memory. When I get to line 27, what happens? Well, just like before, I get a pointer, which I'll draw as this square. It's called T. And what's its value by default? Like, who knows? Some garbage value. So I'll abstract that away as a question mark. And as soon as the right-hand side of line 27 executes, what am I putting inside of T? The same thing that's in S. So if we, for a moment, remove this abstraction of the arrow and we say, oh, well, this is memory address 123. When you say T gets S, semicolon, you're literally putting 123 here. Now, if we kind of simplify our world again with pictures, what you've really done is just added another arrow to your world that's pointing from T to the same exact string. So when in line 31 and 32, I actually go about changing T bracket 0, what is T bracket 0 apparently synonymous with now? S bracket 0. So that's all that's happening. And even though this sort of feels a little low level and arcane, and this sort of feels like perhaps intuitively this should have just worked. I've made copies of things before and it just worked. If you actually think about what a string really is, it's a char star. Well, what is that? It's the address of some character. Then perhaps it makes more sense that when you try to do something super seemingly simple like this, all you're doing is copying a memory address. You're not actually doing anything with the string itself. So even if you have no idea how you would solve this problem in code, high level, conceptually, what do we need to do in order to make T a true copy of S, apparently? Yeah. Exactly. We need to give T a brand new location. We need to somehow create a world in which we get a new chunk of memory, which just for clarity's sake, I'll draw right below this one, but it doesn't need to be there. But it needs to be the same size, so I'll draw these vertical lines in the same place. It's fine if this is all garbage initially. Who knows what was there? But step 1 is going to have to be give me as much memory as I need to fit a copy of hello, then figure out how to copy the H here, the E here, the L here, and so forth. But this already should feel a little obvious, even if some of the details are still abstract. To copy this string into this, it's just a for loop or a while loop or something with which you've become all the more familiar. So let's try this. Let me go into copy2.c. And in copy2.c, we have almost the same program except for line 27. Now, it looks a little complex, but if we break it down piece by piece, the left-hand side is the same. Char star T creates this thing in memory. albeit with a question mark, because we have no idea what's there by default. On the right-hand side, we're now introducing a new function, malloc, for memory allocate, give me memory. And it apparently takes how many arguments? How many things inside parentheses? Yeah, so I heard murmurings of 1 and 2, but it is just 1. There's no comma, which means there's just one thing inside the parentheses. Even though there's other parentheses, let me highlight what's inside of the outermost parentheses, and it's this expression, strlang of s plus 1 times size of char. So if we actually think this through, well, this is saying give me the length of s. Why am I, though, adding 1 onto the length? Exactly. We need space for this guy at the tail, the 6th character, that has no English meaning, but does have special programmatic meaning. So we need a +1 for that, because strlang returns the human expectation of length, HELLO or 5. It doesn't give you the additional null character. So I manually add this with +1. And then this, times size of char. We haven't seen this before. This isn't technically a function. It's a special keyword that just tells you what the size is of some data type on a computer. Because in reality, some of us have 32-bit computers. I have a pretty old computer at home, and it only uses 32 bits to represent pointers. And so if I did size of a data type, it might be 32 bits. But if I'm using my new fancy computer, I might get back a value of 64 bits for something like an address. So in this case, just to be super safe, we're not going to hard code something like, well, what is the size of a char according to what we've said so far? We've pretty much said verbally that it's 1 byte, and that's pretty much true across the board. But again, assumptions tend to be bad. They lead to buggy software if people use your software in ways you didn't intend. So let's abstract this away and just more generically say, I need this many chunks of memory, and each chunk of memory should be equivalent to the size of a character, which is, in fact, equal to 1 in this case, but it's a more generic way of writing it. So if the word is hello, how many bytes does malloc apparently allocate for hello? 6, exactly as many as we have question marks on the screen. And then take a guess now, based on your understanding of getString, what does malloc probably return? An address of what? Of the first chunk of memory. We have no idea what's there, because someone else, some other function, could have been using this memory previously. But malloc, like getString, returns the address of the first byte of memory that it has set aside for you. However, what it does not do is fill in this blank with a \null character. Because it turns out you can use malloc to allocate anything. Ints, strings, arrays, floats, student structures. You can use malloc completely generically. It doesn't care or have to know what you're allocating memory for. So it would be presumptuous for malloc to put a \0 at the end of every chunk of memory it's giving you, because this \0 thing is just a convention for strings. It's not used for ints. It's not used for floats. It's not used for students. And so the gotcha with malloc is that the burden is entirely on you, the programmer, to remember how many bytes you allocated, and not to ever use a for loop or a while loop and go past the boundary of the chunk of memory you've been given. Put another way, as soon as you allocate memory, you cannot ask the operating system, oh, by the way, how big of a chunk of memory was this? It's entirely up to you to remember if you need that value. So let's see how I proceed to use this memory. In line 28, why am I doing this? 28 and 29? Just total sanity check. Just in case something went wrong, I asked for some crazy amount of memory, or I have so many things running on the computer that there just isn't enough memory, something like that, I at least want to check for null. In reality, most computers will give you the illusion that every program can use the entirety of your RAM. But even so, if the user types in some crazy long string, maybe because they're a bad guy and they're actually trying to crash your program or hack into it, you want to at least check the return value of malloc and whether it equals null. And if it does, let's just quit right now, because I don't know what to do in that case. Now, how do I copy the string? There's a few ways to do this. There are strcopy functions in C, but it's super simple for us to do this the old-fashioned way. First, let me figure out what the length of s is. And I could have put this in the loop, but instead I just put it out here for clarity. So n now stores the length of the original string, which is apparently 5. Then in my for loop, I'm iterating from 0 on up to n. And on each iteration, I'm putting s bracket I inside of t bracket I. So that's what I implied with my two fingers pointing at the strings before. As this for loop iterates like this, I'm going to be copying h into here, e into here, l into here, because this is s, this is t. And then lastly, in line 35, why am I doing this? I need to make sure that I'm ending the string t. And I did it this way to be super explicit, but propose someone, if you could, a different way of doing this. I don't really need line 35. There's another way to do this. Yeah? Say it louder. Exactly. We could just say less than or equal to n, which in general has been bad, because almost always when we go up to an equal to the thing we're counting, we go one step too far. But remember, how many bytes did we allocate? We allocated strlen of s, so 5 plus 1 for a total of 6. So in this case, we could do something like this, so that we're copying not just the HELLO, but also the \0 at the very end. Alternatively, we could use a function called strcpy, strcpy, but that wouldn't be nearly as much fun. But that's all it does underneath the hood. Then lastly, we do the same thing as before. I capitalize T, and then I claim that the original looks like this, and the copy looks like that. So let's try this now. Let me go in here, make copy 2. We'll zoom in and run copy 2. And I'm going to type in hello in lowercase. And indeed, I get lowercase hello as the original, but capital hello for the copy. But I'm not done just yet. I need to do one last thing here. 46 and 47 is clearly freeing memory, but what does that actually mean? Well, what am I doing, do you think, by calling line 46 and line 47? What effect does that have? Yeah. Exactly. You are just telling the operating system, hey, thanks for this memory. You can now use it for someone else. And here's a perfect example of garbage values. I have just used this memory to write down the word hello in two places, here, 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 and here. So this is HELLO \0. But then I call line 46 and line 47. And you know what happens there in terms of the picture? Actually, wait, this picture is the old one. Once we make the copy, this guy is actually pointing here. So let's remove the numbers and just abstract away as our arrows again. What happens in this picture when I call free? Not even. If I call free on S and T, kind of a trick question. This picture doesn't change at all, because calling S and calling T just tells the operating system, hey, you can use this memory again. But it doesn't change this to null or some special character. It doesn't change this. It doesn't change the H or the E or the L or the L or the O in either place to anything else. In terms of the picture, as soon as you call free, nothing changes. And therein lies the origin of garbage values. Because if I then later in this program ask the operating system for more memory with getString or malloc or something like that, and the operating system says, sure, I have, 12 bytes of memory just freed up. Use these. Well, what are you going to be handed? You're going to be handed a chunk of memory that we would typically draw with question marks. But what are those question marks? They happen to be HELLO, HELLO. These are our new garbage values as soon as you free up that memory. Now, there's a real-world implication here, too. This happens to do with RAM, but your computers actually do the same thing with disk. We'll talk about this in particular with a future problem set that focuses on forensics. But what actually happens if you have some sensitive, financial file on your desktop or some sketchy JPEG, and you drag it into your trash? What happens when you drag it into the trash or the recycle bin? You knew what I was talking about. What happens when you've dragged that evidence into your recycle bin or trash can? Well, so careful. What happens when you do that? So the short answer is nothing, right? Like sketchy or sensitive file is still just sitting there somewhere in your hard drive. Now, most of us at least have learned the hard way that you need to empty your trash or your recycle bin to actually delete files. And indeed, when you right-click or control-click on your trash can or choose File, Empty Trash, or whatever, and you actually empty the trash can or recycle bin, what actually happens then to this picture? More nothing. So nothing actually happens on disk. And if we just temporarily digress and write, I'll just use the back of this. So now the story is changing from RAM, which is where programs exist while you're running them, to disk, which is where they are stored long term, even when the power goes out. For now, and we'll come back to this in the future, let's just pretend that this represents the hard drive inside of your computer, because back in the day, they used to be circular disks, much like floppy disks. So if you do have some sensitive Excel file, it might take up this chunk of memory on your computer's disk. And I'm just drawing some arbitrary ones and zeros. Now, when you drag the file like that to your trash can or recycle bin, literally nothing happens, because Apple and Microsoft have just decided the trash can and recycle bin is really just a temporary placeholder. Maybe eventually the OS will empty it for you, but typically it doesn't do anything, at least until you're really low on space. However, when you go to empty trash or empty recycle bin, similarly, nothing happens to this picture. All that happens is elsewhere on your computer, there's some kind of table. It's sort of like a little cheat sheet that says that, let's say, resume.doc, so your resume in a Microsoft Word file, used to live at location 123 on your hard disk. Not in memory, and not in RAM, but on your hard disk. And your sketchy JPEG lives at 456, and your Excel file lives at 789, or wherever. When you delete files by actually emptying the trash or the recycle bin, this picture doesn't change. The zeros and ones on your hard drive don't go anywhere. But this table, this little database of sorts, does change. When you delete your resume, it is as though the file is deleted in some sense, but all the computer does is forget where that thing lives on your hard drive. The zeros and ones that compose your resume or any of these other files are still intact. So if you did this accidentally, there's still a non-zero probability that you can recover your data using Norton Utilities or some commercial software whose purpose in life is to find zeros and ones that have sort of been orphaned, forgotten here, but left here so that you can get your data back. Or forensic investigators with the police or FBI would actually take a hard drive and actually look for patterns of zeros and ones that look like JPEGs, look like Excel files, and recover them that way, even if the computer has forgotten them there. So the only way really to delete data, as we'll discuss in the future, is to scrub or wipe the file or hard disk by, you can't really get rid of the zeros and ones, because otherwise you'd start with like a gigabyte hard drive and you'd end up with a megabyte hard drive if you constantly were deleting literally zeros and ones. So what would you do if you really wanted to cover your tracks? And the fundamental problem is that there's still zeros and ones on the disk. I see someone gesticulating that you would physically break the device. That will work. But if that's kind of an expensive solution, what would be more reasonable? Yeah. Overwrite them with what? Other data. You can just overwrite your disk with zeros or ones, or all zeros, all ones. And that's indeed what some of the software does. You can buy software or even get free software. And even built into Mac OS these days, less so in Windows, is the ability to securely erase. Actually, if you want to all run home today, if you have a Mac and do this, if you've got some stuff in your trash can, you can do secure empty trash, which does exactly that. Rather than just erase files here, it doesn't erase the zeros and ones here. Rather, it just changes them all, for instance, to zeros. And ... So one of your future P-sets will actually be to intentionally recover data, photographs that we've taken of people, places, and things on campus, for which we'll make a forensic image of a digital camera's memory card, which is the exact same idea. And you'll have to be challenged to actually find the patterns that represent JPEGs on your hard drive, much like that former student whose email I read a few weeks ago did to recover his sister's photographs. Why don't we take a 5-minute break here, and we'll regroup with more on memory. So here's where things get a little mind-bending, but this is a very powerful step toward understanding this all the more. So here's a program called pointers.c. It's among today's sample code. Notice that in the first few lines, 19 through 22, all we're doing is something called like get string and returning an address, storing it in S. Henceforth, for pset, even 3 if you want, but pset 4 and onward, you can begin to take these training wheels off yourself. There's no reason to pretend that strings exist anymore. Certainly OK to just start saying char star. As an aside, in online references and in books, you may often see the star next to the variable. You might even see spaces around both sides of it. All of those are functionally correct. For now, though, we'll standardize on this approach to make super clear that char star is like saying character pointer. That is the data type. And then the name of the variable is S in this case. All right, so we've gotten a string and we've called it S. And then down here, notice that I'm doing actually a little bit of trickery. This is called pointer arithmetic, which is sort of super simple. It just means add and subtract numbers to pointers. But this actually works. This program apparently prints the string s, one character per line, such that the end result, just so we can spoil where this is going, make pointers, run pointers. Let me zoom in. Now let me type in something like hello, hello, and type enter. And it prints one character per line. Now, up until a second ago, we would have done this with square bracket notation. We'd have a for loop, and we do printf of s bracket I, and we do that again and again and again with a \n at the end of each line. But this program is different. This program is using, literally, arithmetic. So what's going on here? Well, first of all, before this loop even executes, what, just to be clear, is s actually? S is an address. And it's the address of, in the case of hello, the first character in that word, which is h. So s is, in this particular example, the address of h. So what does it mean to do s plus I? Well, I starts at 0 in this for loop. We've done that many times. I is going to go up to the length of the string, apparently. So on the first iteration of this loop, I is obviously 0. So this expression is saying s plus I, rather s plus 0. That's obviously just s. So what is star s here? Well, now we're using the star in a slightly different way. Let me go ahead and get rid of t, because we're done talking about t and copies of s. Now we just want to tell a story involving s. And so at this moment, after having type string, our world looks quite like it did before, with just s, storing the address of h, and more generally, pointing at this string hello. Well, if I now do a line like star s plus I, let's try this out. So star s plus I, well, let me simplify this because this is 0. So this is star of s plus 0. Well, wait a minute, simplify further. This is star of s. Well, now the parentheses are kind of stupid. So now let's just do star s. So in the first iteration of this loop, that line that's highlighted, 26, is pretty much equivalent to printing this. Well, what is the data type of star s? Well, in this context, because the star happens to be next to the s itself, but more specifically, because we are no longer declaring s. We're not creating a variable anymore. There's no mention of char star in line 26. There's no mention of the keyword string. We are just using a variable called s. It turns out now the star has slightly different and admittedly confusing meaning. Star s here means go to the address in s and print whatever's there. So s is here. Star s is sort of like chutes and ladders, follow the arrow here. So this is star s. So what gets printed on the first iteration of that loop in line 26? I print out %c, which is the placeholder for a character, then a \n for a new line. Star of s plus I, where I is 0, is just this. So what char do I place in for %c? H. Now, in the next iteration of the loop, you can probably see where this is going. The next iteration, I is obviously 1. So this means s plus 1. And then now I do need the parentheses, because now the star needs to say, go to memory address s plus 1. Now, what is s? Well, let's roll back in time and say, all right, this arrow now isn't actually doing us any favors. Let's more specifically say that this is storing the number 123 because the start of this string, hello, this is address 123, this is 124, and so forth. So on the second iteration, when I'm saying s plus 1, that's like saying 123 plus 1, otherwise known as 124. So what char gets printed on the second iteration? E at memory address 124. Then plus again, 125, 126, 127. And this loop thankfully stops before we get here because I'm using Sterling to make sure that I does not count too high. So that, too, is it. Again, this is just as though we had done a week ago. Let me write it on the line below, even though this is, we don't want to do both. This is identical now to this. So even though s is a string, as we've been calling it for weeks, s is really a char star. So if we want to be super anal, it's really proper to write the specific character at the ith location using these numeric addresses and this star operator. But frankly, this is just so much cleaner. So this is not bad. No reason to stop doing line 27 here. But 26 is functionally the same. And it's functionally the same for exactly the reasons that we've been discussing thus far. And lastly, 29 is just good practice. Calling free of s means that now you're giving back the memory that getString gave you. Because again, as I mentioned Monday, getString for weeks has been introducing a bug into your code. Your code for weeks has had memory leaks, whereby you've been asking getString for memory, but you've never been giving it back. And that was deliberately chosen by us pedagogically because it's just too much to think about early on. But now we need more symmetry. If you ask the computer for memory, as is the case for getString, as is the case apparently for malloc, you must now, for pset 4 onward, also free any such memory. Notice this is different from saying int n. You do not need to free this because you did not call getString and you did not call malloc. And even if you called getInt, as we'll eventually see, getInt does not allocate memory for you because you can actually pass around integers and floats and chars just the way we've been doing for weeks. Strings, though, are special because really they're the concatenation of multiple chars. So they're just different from chars and floats and ints and the like. But we'll come back to that before long. Any questions then on this beginning of pointers? Yeah? Very good question. So one of the few things C actually does for you, which is convenient, is it figures out for you what the size is of the data type and then does that kind of multiplication for you. This is irrelevant in the case of chars because almost always a char is 1 byte, so this just works. But for the sake of discussion, if you were actually printing integers and you were trying to print out some value s that was pointing at an integer, you similarly would not need to do plus 4 times I just because an int is 4 bytes. Pointer arithmetic means that C and the compiler do all that math for you. All you have to care about is the counting in sort of the human sense. Yeah?
If we declare like strings inside the for loop, we have to free it on later.
Good question. If you declared a string inside of the for loop, do you need to free it later? So you only need to free memory that you allocate with getString or with malloc. So if you just say something like, let me put curly braces now so all the code is related. If you did something, albeit buggily, like this, char star t gets s, you don't need to free t because t did not involve any mention of malloc or getString. If by contrast you did this, getString, then yes, you would need to free t. And in fact, your only chance to do that is now inside this loop for the same issue of scope that we've discussed in the past. Otherwise, you'd be allocating memory, allocating memory, allocating memory. And at the end of the program, because you're outside of that loop, t doesn't exist, but you never told the operating system that you didn't need that memory anymore. And before long, for pset 4 or 5, we'll equip you with a program called Valgrind, which is similar in spirit to GDB, in that it's got somewhat of an arcane interface, but its purpose in life is to help you. And Valgrind is a program that will, in the future, search your programs looking for memory leaks, whether from getString or malloc, which we'll start using all the more as we stop using the CS50 library as much. Well, we finally now have sort of the vocabulary and the sort of mental model, in theory, with which to solve this broken program. So in this broken program, swap worked inside of swap, but it never actually worked in main, because main passed in x and y, recall, and those were passed in by value, so to speak. Copies of them were given to swap. By the end of swap, A and B had indeed been exchanged, but of course x and y, as we discussed on Monday, had not been. So I propose in green here that this is actually the solution here. And actually, let me move my stars just to be consistent, even though, again, functionally this doesn't matter. And in the future weeks, we'll explain when and why it does matter. So in green now is a solution. Frankly, it looks a whole lot messier because I have all of these stars. And let me point out one thing. The top line here, where it says int star A and int star B, is fundamentally doing the same thing as it always has. It is declaring 2 arguments or parameters to swap, the first of which is an int pointer called A, the second of which is an int pointer called B. The only thing that's new at this point is the fact that there's a star there. What does that mean? A is not an int. B is not an int. A is the address of an int, and B is the address of a different int. Now, down here, this is where I admit C gets confusing. Now we're using a star, but it has different meaning in this context. Because we're not declaring pointers as we are up here, here we are dereferencing things. So technically, the star in this context of the first, second, and third line inside of swap is the dereference operator, which just means go there. So just as my finger followed the arrow to H, star A means go to that address and find me the int that's there. Star B means go to the address and pass me what's there. So let's redraw the picture from Monday, now using, again, a stack of frames, the bottom one of which is going to be main, the upper one of which is going to be swap, so that our world looks just like Monday, like this. Here is a chunk of memory that main is going to use. And recall from Monday that the program just had two variables, one called x and one called y. And I'd put the numbers 1 and 2 there. Now, when I call swap, like I did on Monday, previously when I used the red version of this program, which looks like this, I got two parameters, a and b. And what did we write here and here? Just 1 and 2, literally copies of x and y. Today, we changed that. Today, instead of passing in ints, a and b, we're going to pass in two addresses. Those addresses happen to point to ints, but those addresses are not ints themselves. They are addresses. It's like a postal address instead. So now we need to just give myself a little more detail on the screen. This is my computer's memory, as it's been all day. Now we need some arbitrary numbering scheme. So let's just say, just by chance, that this is memory address 123, 124. Let's just say this is 125, this is 126, and so forth. But that's totally arbitrary. We just need some numbering scheme in my memory. So now, when I actually pass in x and y, I'm not going to pass in x and y. I'm going to pass in the postal address, so to speak, of x and of y, so that what gets stored here and here is not 1 and 2, but if you can see my small text, what gets passed in here and here? Exactly. 123 gets put here, and 124 gets put here. Now, because I used the star in this very first line, way up here at top, my program just knows that 123 and 124, even though they're obviously integers that any human could notice, they should be interpreted as addresses, numeric addresses. They are not in and of themselves ints. They're addresses, and that's because I have explicitly put the stars there. So now, in my first, second, and third line of actual code, what happens here? Well, let's draw the rest of the picture. Temp is just like it was on Monday. Nothing special about temp. It is just a local 32 bits variable. And inside of that, I'm apparently storing the value of star a. Now, if I just said temp equals a, what would I put here? 123. But that's not what I'm doing. I'm saying temp equals star a. Star means go there. So here is a. 123, how do I go there? Pretend like there's an arrow. Well, there it is, 1. So what gets stored in temp apparently? Just 1. So in other words, temp is star a. Star a means go to the address that's currently in a, which is apparently 123. OK, here we are at location 123. I see the number 1, so I'm going to put the number 1 there. Now what do I do in line 2? Star a equals star b. This one's a little more involved because now what is a? It's 123. So star a is where? Right where I was before. So go there. OK, now lastly, and then finally this will start to make sense hopefully, star b means, OK, what's in b? 124. So I need to go there, which is 2. So what do I put where? 2 goes into here because star b goes into star a. So I'll do that. And you can already see perhaps that we're so much closer to solving this stupid, simple problem correctly for the first time, because now we still have a recollection of what x was. We have two copies, admittedly, of y. But line 3 now says star b. So here's b. Star means b means go there. So where's location 124? It's apparently here. So what do I put here? Obviously, temp. So now I do this. So I have 1 here and 2 here. And now what about all of this? The 123, the 124, and the 1. As soon as swap returns, this memory is as good as lost, because as soon as swap returns, the operating system is free to use that memory again in the future. Only main's memory at the bottom of this so-called stack sticks around. And so we finally have now a working version. Let me go into swap.c and notice the following. At the top of the program, I've changed my prototype to be int star A and int star B. So the only thing I changed to go from red, which was bad, to green, which is good, is I added these stars today. But then down here in swap itself, I had to copy paste what was just on the slide. I have a star here, that matches the prototype. And then all of these things now have stars except for temp, because the use of a temporary variable, there's nothing new there. I just need temporary storage for an int. So we don't need a star there. We just need the star so that we can cross this sort of arbitrary boundary between these two frames in my computer's memory. But one last thing has to change, and you might have glimpsed it already. What other line is obviously different now? Yeah, so 25 is the last line of code I need to change for this to work. A week ago, and even on Monday, line 25 looked like this: swap x and y. And this was just broken, because if you say swap x comma y, you are giving copies of x and y to swap, then it's doing its thing, but you're never actually changing x and y itself. So even if you've never seen this character before, the ampersand in code, just take a guess. What does the ampersand do, apparently? Takes the address. So the ampersand is saying, give me the address of x. Who knows where it is? Happens to be 123. I don't care. Just give me the address of x. Ampersand y means give me the address of y. And at that point, the story is perfectly consistent with the picture we drew a moment ago. So I'll admit it, pointers, certainly for me when I first started learning this, were definitely one of the hardest things to wrap my mind around. But realize, especially as we keep playing with these kinds of things, if you break it down to these super simple, sort of intellectually uninteresting problems of just moving numbers around, the answer to a lot of confusion with pointers really can be derived from these very basic mechanics. Here's an address, go there with the star. Or conversely, here's an ampersand, figure out what the address actually is. All right, so where is all of this memory coming from? So we've drawn this picture a couple of times, and I keep promising we'll come back to it. But here's the representation of your computer's memory that's a little more labeled than our chalkboard here is. The text segment at top represents what with respect to your program? Sorry, say again? The actual program. So the zeros and ones that you have compiled after writing C code and then running Clang and generating zeros and ones ends up getting tucked there in memory, because when you double-click an icon on your Mac or PC or run a command like Mario at your prompt, your zeros and ones from disk get loaded into memory so that the computer can manipulate them and execute them more quickly. So initialized data and uninitialized data, we won't talk much about those, but those are just global variables. Initialized means global variables that you gave values to. Uninitialized means global variables that you did not yet give values to. Then there's these environment variables, which I'll completely wave my hand at, but they are there. And that stores things like your username and other sort of lower level details. But the juiciest pieces of your memory's layout is this thing called the stack and the heap. So the stack, again, to be clear, is the memory that's used whenever functions are called, whenever there are local variables, and whenever there are parameters being passed around. All of that happens in the stack. The heap we haven't talked about, but take a guess who uses the heap. Just a different chunk of memory, happens to be drawn here at the top, but that's an arbitrary pictorial convention. Who's apparently been using memory from the heap for weeks? It's technically you, but indirectly. GetString and malloc. So here's the fundamental difference. You know for the past few weeks that if you need memory, just declare a variable. If you need lots of memory, declare an array right inside of your function. But the problem we've kept facing is if you declare variables locally inside of functions, as soon as the function returns, what happens to them? What happens to the memory and those variables? Just sort of, it's no longer yours, right? It just disappears sort of conceptually. It's still physically there, obviously, but it's no longer your right to use. This is obviously problematic if you want to write functions in life that actually allocate memory and don't give it back immediately. Case in point, getString's purpose in life is to have no idea in advance how big of a string I'm going to type at the keyboard, but it's got to be able to allocate memory to hold DAVID or HELLO or a whole essay that the user might have typed in. So getString has been using malloc. Malloc, therefore, must be using not the stack. Instead, it's using this thing called the heap. There's nothing different about the memory. It's not faster or slower or anything like that. It's just physically in a different location. But the rule is that the memory that's allocated on the heap will never be taken away from you until you call, take a guess, free. By contrast, any memory you ask for on the stack, by just declaring an array or declaring a variable like we've been doing for weeks, that by default ends up on the stack. And that works great 90% of the time, but on those rarer occasions where you want to allocate memory and keep it around, well, then you need to use a function like malloc. Or we have used a function like getString, which in turn uses malloc. Well, let's see where this might break down and then take a peek at Binky. We'll come back to that in the future. So here is a super simple program that in the first 2 lines does what? In English, what do these first 2 lines of code do inside of main? Careful. It doesn't give me the address of x or y. Good. Give me 2 pointers to integers. In other words, give me 2 chunks of memory that I keep drawing today, even though I erased it now, as squares. Give me 2 chunks of memory, one called x, one called y. Earlier I called them s and t. And what is the type of that chunk of memory? It's going to store a address. It's of type int star. So the address of an int will eventually live in x. The address of an int will eventually live in y. But initially, what's inside of x and y? Who knows? Garbage values. Has nothing to do with pointers. If we haven't put something there, who knows what's actually there? Now x, what happens here? Well, this is legit now because x is a pointer. It's an int star. So that means I can put in x the address of some chunk of memory. What does malloc return? Perfect. It returns addresses. The address of the first byte in a whole chunk of memory. How many bytes is this apparently allocating? For instance, in the appliance, what's the size of an int? 4, right? If you think back to week 1, it's not super important to always remember that, but in this case, it's useful to know 4 bytes. So this is allocating on the heap 4 bytes, and it's returning the address of the first one to me arbitrarily. Now, what is x doing? Well, x, a star x equals 42, is doing what? Well, if at this point in the story, we have x, which looks like this with some garbage value. This is now y with some garbage value. Now in line 3, I've allocated 4 bytes. This picture essentially looks like this. Or more specifically, if this is arbitrary address 1, 2, 3, this is what our story now looks like. Y, meanwhile, star x equals 42 now means what? That means go to the address 1, 2, 3, and put the number 42 there. Now, I don't need to draw these lines because we're not doing strings. I should have just written it like this. And just for demonstration's sake, 42 is an int, kind of takes up a lot of space, 4 bytes. So that's what's happened there. But there's a problem now. Star y gets 13. What's going to happen here? Well, the problem is star y, in our simplified world, just means go to the address in y. Well, what's in y? It's some garbage value. So let's assume that that garbage value is like 5551212, something crazy like that. Star y means go to address 5551212. That's like over here. Doesn't exist, for instance. So star y gets 13 means I'm trying to draw 13 here. It doesn't exist. I've exceeded the segment of the blackboard. What do I get? That cryptic message segmentation fault. Because I'm trying to put in memory a value like 13 at a place that doesn't exist. The rest of the program might work OK, but up until that point, it doesn't. So let's try to tell this story. We'll come back to that once we've talked about hex. Let's go back to this and conclude with this link at Binky, which recall is a Stanford professor sitting at home playing with claymation to tell the story of exactly that same program. It's just about 3 minutes long. Here we have Binky.
Hey, Binky, wake up. It's time for pointer fun.
What's that? Learn about pointers? Oh, goody!
Well, to get started, I guess we're going to need a couple pointers.
Okay, this code allocates 2 pointers which can point to integers.
Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything.
That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step.
Oh, right. I knew that. The pointees are separate. So how do you allocate a pointee?
Okay, well, this code allocates a new integer pointee, and this part sets x to point to it.
Hey, that looks better. So make it do something.
Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing.
Your magic wand of dereferencing? That's great.
This is what the code looks like. I'll just set up the number and...
Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, Try using it to store the number 13 through the other pointer, y.
Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa!
Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it.
Good point.
Yeah, we allocated the pointer y, but we never set it to point to a pointee.
Very observant.
Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x?
Sure, I'll use my magic wand of pointer assignment.
Is that going to be a problem like before?
No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another.
Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over.
Okay, here goes.
Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13.
Yeah, sharing, whatever. So, are we gonna switch places now?
Oh, look, we're out of time. But just remember the 3 pointer rules. Number 1, the basic structure is that you have a pointer, and it points over to a pointee. But the pointer and pointee are separate, and the common error is to set up a pointer, but to forget to give it a pointee. Number 2, pointer dereferencing starts at the pointer and follows its arrow over to access its pointee. As we all know, this only works if there is a pointee, which kind of gets back to rule number 1. Number 3, pointer assignment takes one pointer and changes it to point to the same pointee as another pointer. So after the assignment, the 2 pointers will point to the same pointee. Sometimes that's called sharing. And that's all there is to it, really. Bye-bye now.
This is Binky. This is CS50. We'll see you next week.